Our first speakers of the morning, who are John Nunez and Jay Smith, with their talk, Mainframe Hacking for Kicks and Giggles.
Thank you, everyone, for being here. I know some of you were probably at LobbyCon late last night, and some of you might be hungover, so thank you for getting here early. As the slide says, this is a talk about... Oh, testing. Oh, there we go. All right, thank you. So as the title of the talk suggests, this is about mainframe hacking, specifically around CICS applications. Most of the talks in this area have been around the system side, but this is primarily focused on the application side. So we have a few housekeeping items to cover before we really get going. The first one is that if you've never worked with mainframes, this is going to feel like drinking from a fire hose. That's how it felt for us. And due to that, we are not going to cover a lot of system level concepts. So we're not going to talk about ZOS, VTAM, JCL, none of that stuff. It's just mainframe overview and then specifically things around applications. This next one is that we are not mainframe experts. We're security researchers who were tasked with looking at mainframe applications and how they work. We didn't know anything about mainframes when we started this, so if you're an operator or a developer or a longtime user, please cut us some slack. We're not mainframe guys. We're hackers. And then the final one is a disclaimer that we're obligated to put by our employer, and it's just what it says. We are not here on behalf of or representing our employer, and anything that we say or do is our own views and not those of our employer. All right, with all that housekeeping out of the way, a little bit about the team. My name is Jay Smith. I've been doing IT for about 25 years. I've done everything from help desk to systems engineering, network engineering, NOC work, SOC work, development, and now I am a lead security researcher for my company. My current research focuses around mainframe systems, IVR systems, and MQ.
I'm John Nunez. I got my career started in software development, then information security compliance, eventually got into pen testing. Since then, I've specialized in web apps, API, pretty much anything HTTP, some mobile apps, and most recently, mainframe applications. We're excited to talk to you all about today.
And then the last member of our team, Garland, could not be here today, but his contributions were invaluable for reasons that we will get to later, so we want to make sure that he does get due credit for the research. All right, so before we start talking about the applications, we just want to level set about mainframes in general. So a show of hands, who here has worked with a mainframe as a developer, operator, user? Okay, a few of you. How many of those within the past 5 years? Not as many hands. All right, that sounds about right. And then how many people here have done a security assessment on a mainframe? Okay, a few. Some of the hands are the same, but not most. All right, and that's kind of the same boat we were in. We're just security guys who had to look at a mainframe. So for those who didn't raise your hand, when we say mainframe, this is often what people think. This legacy, archaic system, like a proverbial dinosaur of computing. I've talked to people and they'll say, hey, I used to work with those in the 80s or 90s. Are those things are still around? Or maybe you think of this, like this giant machine that takes up this whole room and requires a team of people to operate, like Joshua from War Games. Well, the reality is that today they look like this. This is a Z16 mainframe, top of the line, just came out last year. It is one of the most powerful commercial computers you can buy. It runs anywhere from the high 6 to low 7 digits. And it runs a modern operating system known as ZOS, the most recent version of which came out last year. So this is modern hardware running a modern operating system. There is nothing legacy about this at all. And whether you realize it or not, you rely on these systems all the time for everything you do day to day. If you have withdrawn money from an ATM or paid for something with a credit card, if you scanned a check for a mobile deposit or booked a flight or paid your taxes, anything like that, you have relied upon a mainframe. They have been and continue to be the backbone of many industries that we rely on as society today. Industries such as finance and banking, healthcare, insurance, utilities, government, all of these industries could not work without mainframes. And there's a few reasons for that. The simple answer is they are very, very good at what they do. There is a reason that they command the price that they command. So a few examples of that. A modern mainframe can process roughly 19 billion encrypted transactions per day. To put that into some perspective, that's the equivalent of hundreds of Cyber Mondays per day per single machine. They have mean time between failures measured in decades and have uptime of years, also sometime of decades. You can take an application that was developed in the 70s or 80s and drop it on a modern ZOS system, and it's just going to run right out of the box with no issues. That's like taking a DOS or a Windows 3.1 application and running it on Windows 11. So these are very, very powerful and useful machines. And unfortunately, that makes them high-risk systems. It's not an exaggeration to say that if mainframes were to stop working today, for whatever reason, it would be global economic pandemonium. They are that critical to our infrastructure. And unfortunately, they are not tested often enough or thoroughly enough. When I asked the question about who here's done a security assessment, there was maybe 5 people in the whole room that raised their hands. And that should be way more. So now that we've level set, that's all we're going to talk about for the mainframe side. Now we're going to focus on the application side. Now the first thing to understand about mainframe applications is how they differ from a traditional distributed system. So let's say you have a web application. You probably have an application server, a database server, a logging server, an authentication server, and you have all of these disparate servers that are working together to support the operation of that application. Well, in a mainframe, everything is self-contained in the mainframe itself. There is no distributed components to it. It's all this monolithic machine that does everything in-house. And it does that through subsystems that are contained within the mainframe. Now, we can broadly categorize the applications into 2 camps. The first one is batch processing applications. So with these applications, you have some input, it goes through some kind of data transformation, and then you get some output. So if you're a regional sales manager and you want to consolidate the nightly reports for all of your regional stores, a batch process could do that. The time that these take is a function of the work to be done, and these can process terabytes of data. So you can have a batch process that runs for minutes, hours, or even days. And the key takeaway is that this is not something that an end user will submit and then get an immediate response back. This is something that is just either automatically kicked off or kicked off as a back-end process, and then it just runs until it's done. In contrast to that, you have online transaction processing, or OLTP. And this is the style that you're probably more familiar with. This is when an end user goes and does something and then gets an immediate response back. So I'm a loan officer and I want to look at this person's loan account information. I put in their account number, I immediately get a response back with their account information. I want to make changes to it, so the terms of the loan or contact information, whatever. I submit those, I immediately get a response back saying those changes have been saved. So the most common OLTP system is CICS, the Customer Information Control System. And this is actually a subsystem that supports the running of mainframe applications online. So this subsystem handles everything. It handles communication with all the other subsystems. It handles the management of shared resources, the integrity of the data, responding to each individual concurrent user. Basically everything necessary to run this application is handled by the CICS subsystem. And you can think of these as web applications before the web. And it's a rough analogy, but it helps us understand some of the terminology used. So when you're working with a CICS application, the terminal is your web browser. So if you want to go to the CICS application, you're using a terminal. And there's a few other interfaces you can use, but primarily an end user is going to do it this way. Now once you're on that CICS application, or once you're on the terminal, you need to know where you want to go. In a website, that would just be your URL, www.google.com. In a CICS application, that's your region. So you need to know what region you want to log into. So in the example here, DVCA prod is the region that we're logging into from our terminal. Well then once you're logged in, you need to know where on that website you would want to go through. So for instance, using the Google analogy, /mail to get to your mail. Well in a CICS application, that's known as your transaction. And it's a 4-character alphanumeric transaction ID. So once you log into your region, you would type in your transaction, and that's how you get to it. And you can go to any transaction that exists on that region, provided you have authorization to do so. Now, as I mentioned, there are multiple ways to interface with CICS. Most of these other ways are back-end processes utilized by front-end systems. So you have Java applets, web services, RPC calls, native mobile applications, all of these other ways for a front-end system to interface with CICS on the back end. And you may not realize it, but a lot of websites that you do use interface with CICS on the back end. So it's a very, very prevalent subsystem. Now, unfortunately, CICS applications suffer from this concept of a legacy code base with modern infrastructure. So I mentioned earlier that you can take an application that was developed in the 70s or 80s, drop it on a modern mainframe, and it's just going to run right out of the box. And that's fantastic for support or operations. It's terrible for security, because many of these applications were designed at a time where nobody was thinking about security. And we have talked to and met with developers who've said things like, the person who designed this retired 10 years ago, we're just kind of keeping it going along. We don't actually know how all this stuff works. Or we've seen applications that have not had a single code release in 10 plus years. So this is a very, very prevalent problem with these applications. Now I'm going to turn it over to John, who's going to talk a little bit about the testing side and our research.
Great. So at this point in our research, CICS became an obvious candidate for testing mainframe applications. But we ran into a number of challenges. I know we have some mainframe developers and operators here, so I don't mean to upset anyone, but mainframe developers can be difficult to deal with. Not all of them, of course, but due to fear of downtime, they are not going to be happy with you poking around their systems. And these systems can be easy to bring down, especially if you don't know what you're doing, which we know from experience.
Yeah, you get that call from a mainframe operator really quick when you bring down their system.
Another challenge was getting our hands on a mainframe for research. A ZOS license can cost thousands of dollars. Mainframe hardware can cost hundreds of thousands of dollars. IBM does have alternatives for development and testing, known as ZD&T, but a personal license costs $6,000, and this is for a year. A perpetual license costs closer to $13,000. They did have a learner's edition, but it's no longer available, so we're not going to get into that too much, but it was about $120 a year. It did require prerequisite courses or proof of 1 year as a mainframe engineer, and there was a backlog of about 6 to 12 months before you can actually purchase it. Another challenge was the lack of tooling. If you're testing a web application, you probably use Burp or all these other tools that we've come to depend on, but there are very few tools for mainframe testing. In fact, most of the tools that we experimented with were developed by just 3 researchers, Phil Young, Dominic White, and Ayub, the creator of CICS. These guys have done amazing work, so we want to make sure that we shout them out and give them credit before we get into our own research, and we'll have links to their GitHub repositories towards the end of the slides and in our Discord channel. Perhaps the biggest challenge was the massive learning curve. None of the major cybersecurity training and certification bodies offer content related to mainframe testing, so you're kind of on your own. And you might say, okay, I'll just read the docs, except when it comes to mainframe, this might mean reading through 50 years worth of documentation. Okay, so at this point we had 2 things going for us. We had no idea what we were doing and limited to no reference material. So we did some digging and eventually came across the 3270 Data Stream Programmer's Reference. This was the official reference manual for developing 3270-based applications. It has since been, it's been out of print for decades. You can still find it online. IBM hosts it, and you can even find it used on eBay if you prefer a hard copy. I like to think of it as one of the first API specification documents, maybe ever. And it had everything we needed to start mounting attacks on CICS. And here's what we learned. So the CICS terminal, or the 3270 terminal, is a block mode terminal, which means anything you change on the screen is only sent back to the mainframe when you press an attention identifier key. So this can be any of one of 24 function keys, the enter key, the clear key, and we'll get into these more in a bit. See how you can click anywhere on the terminal and it doesn't matter if there's data, if there's a field, or if it's just some random empty spot? This is because each character position on the screen corresponds to a location in the screen buffer. I like to think of the screen buffer as the terminal's RAM, and it stores all the data that is displayed and instructions on how to display it. Traffic over the mainframe, traffic between the mainframe and the terminal occurs over the TN3270 protocol. And this was IBM's way of adapting to the prevalence of TCP/IP and personal computers, because before that, mainframes required the use of a dedicated terminal that was physically attached to the mainframe via coax. So IBM's solution was to wrap the 3270 data stream in Telnet and call it TN3270. This allowed for mainframes to be accessed over TCP/IP and allowed for the terminal emulators that we use today on any PC.
You can analyze this traffic in Wireshark just like you would any other protocol. In fact, it's not uncommon to discover sensitive information that's sent to the terminal but kept in hidden fields and never displayed. This was a step in the right direction, and it was interesting, but in order to make some of the more interesting test cases possible, we needed a deeper understanding of the 3270 protocol. Fortunately, it didn't take much to get there, and everything we needed was in Chapter 4 of the reference manual. All right, so there's two characteristics of the 3270 data stream that started to make some of the more interesting test cases possible: orders and field attributes. An order is an instruction or a command that we send to the terminal, like this is a field and this is where I want you to position that field on the screen. Each order corresponds to a specific byte value. So in this example, we see that the first byte is equal to the hex value 11. So we know it's a set buffer address order, and as the name implies, this sets a field's location in the screen buffer and as a result on the screen itself. The 2 bytes that follow are just parameters to the set buffer address order that specify the exact location on the screen. But the one we were interested in was the start field order, because not only does this indicate the start of a new field, it also indicates the start of a field attribute, which is the byte right next to it, and it's always the byte right next to it, according to the reference manual. There are other orders that can specify the start of a new field, like the start field extended, but the way we parse the attributes change. So the byte right next to it tells you how many key value pairs there are, and the second and third bytes would be the key value pair for that attribute. We're going to focus on the start field order and the field attribute byte. So I'm going to draw a comparison to a technology we're all familiar with, just to continue that analogy. I like to think of the start field order as an HTML input tag, and the field attribute bytes as HTML attributes for disabling and hiding an input tag. So to continue that analogy, whereas a browser renders HTML that's transferred over HTTP, a terminal renders the 3270 data stream that's transferred over TN3270. And hopefully this starts to make things click for you. All right, so we're going to focus in on the field attribute byte. Each highlighted bit in this byte has something to say about how that field is displayed or rendered. The bit in position 2 determines whether the field is protected or unprotected. In other words, can a user make changes to it in the display? The bit in position 3 determines whether a field is alphanumeric or numeric. And the bits in positions 4 and 5 work together to determine whether a field is hidden or displayed. We were particularly interested in bits 2, 4, and 5, because if we could intercept this traffic and flip these bits so that protected fields become unprotected and hidden fields become visible, then we would have viable test cases for testing mainframe applications. And we're here today because it worked. All right, so we even have some bonus attacks. So not only are we disabling field protections and discovering sensitive information in hidden fields, we're also brute forcing application level secrets and enumerating through all the known attention identifier keys. So before we get into our demo, I should mention that the 3270 terminal is incredibly finicky, especially if you're running it in a Docker container that's also in a VM. So we knew it would be a bad idea to do a live demo, but we're going to do it anyway, so wish us luck.
We're going to try. So before we get started with the demo, just to set some background on what we're using. So traditionally, this kind of research was done via what's known as MVS 3.8. So the ZOS license is generally unattainable for individual researchers for reasons that John enumerated on, but you can use MVS 3.8, which is a precursor to ZOS. It is perfectly legal to use, there is no problems, you won't get in trouble, and there's many ways of getting it. It can be run in an emulator known as the Hercules emulator. Now, when people are first starting to do this, what I always recommend is to use the TK4, that's the Turnkey 4 system, which is basically all of this stuff just packaged together in a single file. You just unzip it, launch it, you're up and running. There is also, in my opinion, a better menu than what comes with it by default, known as ISPF. That second link at the bottom is a Docker container I created that has all of this packaged with ISPF, and you can just download the Docker container and you're up and running with your own mainframe. The thing is, though, this is geared more towards just learning how mainframes work. It has nothing to do with security testing at all. So we worked with Soldier of Fortran, who some of you may know, and he released DVCA, which is Damn Vulnerable CICS application. And it's exactly what it sounds like. It is an intentionally vulnerable CICS application for you to just go crazy with. It is a Docker container, so it's just a matter of pulling the Docker container, exposing 3270 to the host machine, and you're up and running in less than 5 minutes. And that's what we're going to run this demo on. And then the other thing that we want to talk about is the CICS pen testing toolkit. So this is our toolkit that was developed for testing CICS applications. When I mentioned earlier that Garland was an integral part to our research, this is why. He was the one that developed this tool, and he did it over just a few days because he's insane. It's developed in Python, and it basically acts as a proxy for C3270 or X3270. It allows you to intercept based on specific field attributes that John talked about, so sort of like burp, where you can just determine what you want to intercept on. It does have logging capabilities, but it's also very much in an early phase. So this is more a preview of what we're working on. We're working on releasing this tool, that's our plan, but as John mentioned, things are very finicky, so we're not doing it yet, but we are going to try and demo the tool as is. All right, so can you hear me on this? Can you hear me on this? All right, cool.
What's up?
All right. So right now, this is just a colleague VM, and we're running Docker. So we're running the DVCA image in a Docker container. So what we're going to do is we're going to start our CICS pen testing toolkit, and basically we just tell it the IP address of the mainframe server we're trying to connect to.
Pull it closer to your face and try to put it where you're talking.
Oh, there. Okay, there we go. Sorry. All right. You just point the IP address to your mainframe. Since this is a Docker container on localhost, it's just 127.0.0.1. And you can see here that it's waiting for the connection. So it's now acting as a proxy, waiting for you to connect to it so it can send your traffic to your mainframe. So now we're going to launch C3270 and route it through the tool. Whoops. Sorry, wrong port. All right, so now you see that it's detected that we have connected to the tool. And this is the equivalent of burp where its intercept is on, so it's waiting for you to click on something. So we click to continue. Now we're logged into the mainframe Docker container going through the tool. And this is Soldier of Fortran's DVCA tool. So when you go, you just type in DVCA. And you can see here that it's going to launch the CICS application automatically. You don't have to do anything. And then now that CICS application is up and running. So we clear our screen, we go to our transaction, and this is our vulnerable application. All right? So again, we are going through our proxy tool to access this container. And all of this stuff at the top, this is the tool. Now I'm just going to do a quick walkthrough of the application itself, and then John's going to talk about the hacking part of it. So this is just an office supply program. It's something that exists in pretty much any sales system. You know, it's just used for shipping and receiving. So we go into the first menu, we just see office supplies. So you have 3-hole puncher paper. You can get Dom Perignon for $85,000. 24K gold MacBook Pro, or a haunted idol. So a lot of things in here to order. Then we have the shipping address. So this is the address of the customer. The idea being there's this supervisor code down here. So the idea is that you don't want just any random person changing the shipping address to their address and then ordering a bunch of stuff. So you need an authorization code to make that change. So if we try and make these changes, we get this invalid supervisor code because we don't know what the code is. And then the last one is the order history, which is just what it sounds like. This is the items that have been ordered since the container was built. All right. And now I will turn it over to John, who will demonstrate the tool.
Fingers crossed.
Okay. So our tool is up here on the top. We have 4 tabs currently. A lot of the functionality is still under development. The key functionality being the hack field attribute. So as I mentioned, we're effectively intercepting the field orders or the orders in the 3270 data stream. I mean, that would correspond to the field type. So here's the start field order to start field extended and so on. And then we have here, we can choose between the specific bits in that field attribute byte. So we can choose to disable field protection. We can choose to enable hidden fields. We can also choose to remove numeric only restrictions. And we toggle that by clicking on the hack fields button. We have an inject to fields tab, which allows us to perform brute force or automated attacks. So you can select a payload list using the file key here or button. We can set up that payload list, and then we can run the injection. We can also choose a mask character to identify the exact field that we want to target, and I'll demo that in a bit.
You can think of this as the intruder tab in Burp.
Right. Remember I mentioned that the terminal emulator is a block mode terminal, and it only sends data to the mainframe if an attention identifier key is pressed. These are all of the known attention identifier keys, and what send keys will do is it'll automatically send all of these attention identifier keys in hopes of discovering hidden functionality. And it's not a stretch of the imagination to think that a mainframe developer, decades ago would have hidden functionality in some of these obscure 8 keys, especially today where we don't have 24 function keys on a modern keyboard. And not so much out of malicious intent, possibly just to facilitate maintenance and production. And then the tool does have extensive logging capabilities. We'll go through that after our first test case. So let's start the demo. All right, so the first thing I'm going to do is I'll change the shipping address. Let's go into menu option 2. So as Jay mentioned, I try to submit a change. It doesn't allow us because we don't have a valid supervisor code. So I'm going to go ahead and make some changes. Doesn't really matter. Okay. Let's not send that to Canada. USA, okay. So again, I try to submit the change, doesn't work. We don't have a valid supervisor code. I'll try some common options, 1111, doesn't work. 1234, doesn't work. All right, so we have some options. We can go into our inject into fields tab. I'll select a payload list. It's just a word list of all possible permutations for a 4-digit code. So you would have 10,000 different options there. So I'll select the payload. I'll then select our mask character, which will use a $sign. I'll click setup. So now the tool is ready to identify that mask character and know which field we're attempting to target. So I'll submit a test transaction with the mask or with the mask character. And now we see that the tool found the field. So I'll go ahead and click inject. And now we're iterating through every possible supervisor code in hopes of finding one that works. And we can see that up here on the left. Okay, so we're at 20. And I think we shortened this to about 50. Yeah, so just to make things easier. This can take anywhere up to an hour depending on how long your payload list is. Okay, so there we go. We found a valid supervisor code. And the valid supervisor code was 1337. So I'm going to go back to the main screen. Okay, I'll go back in to make sure that our changes persisted, and there we go. We were able to submit an address change by brute forcing a supervisor code. And these types of attacks are incredibly common in CICS applications. So we'll go into our supplies menu option. And we see that we have the printer paper. I'm going to click F7 to go to the next one. We have, sorry, F8. We have, okay, we have 3-hole punched paper. We have, so as we mentioned, the terminal can be finicky. Yeah, all right. Okay, we have the bottle of rosé, we have the MacBook Pro, and we have an ancient golden idol that's haunted. Right, I'm going to try and purchase this ancient golden idol, and we see that it's denied. So we're going to go back into our Hack Fields tab and enable these fields in hopes that we find hidden fields on this screen. So I toggle it, and we see that there's this hidden purchasable field. I'll go ahead and toggle it again so we can see that. There's this hidden field, and what the tool is doing, it's intercepting that the traffic between the server and between the mainframe and the terminal, and it's flipping those field attribute byte bits. So I'm going to change this from N to yes. I'll submit, and we see that now we're able to purchase the ancient golden idol thanks to that hidden purchasable field. So I'll go back. Let's purchase the 24-karat MacBook Pro. I'm going to turn off the hacked fields just to demonstrate that without the hack fields set to on, we can't make changes. Notice that it's X protected down here, meaning that these fields are protected. It does not allow for end users to change it. So I'll go ahead and toggle hacked fields. We have our disable field protections on. So now we should be able to go in, and despite these fields being protected, we should be able to make changes to them. So we'll change it from 20K to something more reasonable. We'll from $165 to $1. Purchasable is already set to yes, so we'll go ahead and try and purchase this. Submit, and we see that we were able to purchase the 24-karat MacBook Pro, ideally for $1. We'll go back. We'll celebrate with a bottle of rosé. Our hacked fields are set to on, so we should be able to modify this. Let's do $5. Okay, we changed the shipping cost from $250 to $5. I try to purchase it, and we get denied because purchasable is set to N, so we go in, change it to Y, and we were able to purchase the bottle of rosé. So we'll go back to the main screen now. Yep. Yeah.
This is what working with 3270 is like. And we get an add-in. Okay.
You want to try to spin it up again?
Yeah. Demo gods at their finest.
We almost got through it. There we go. All right, so we go back to, let's go to the order history and confirm that our changes or that our purchases were successful, and there we go. We have the ancient golden idol. We have the gold MacBook Pro that we purchased for $1. We have the bottle of rosé that we purchased for $5. So now we need to cover our tracks. Go back to the main menu, and we'll use the Hack Fields button again to see if there's anything hidden on the main screen. And we see that there's this Delete Order History menu option. It's set to 99, so I wonder what that'll do. We submit the menu option 99, and we see that we were able to delete 8 records from history. So we'll go into the history menu option to confirm. And ta-da, our tracks were covered. The audit trail of purchased items were deleted, or was deleted. Okay, so now let's do our last test case.
Can you get closer to the microphone, please?
Yep, we'll run through our last test case now. I'll go to the enumerating of attention identifier keys.
Now, you see we've specifically excluded PF1, PF3, and PF5 because those are valid function keys to navigate through the application, and we don't want it to be moving through everything while it's enumerating.
Otherwise, it'd be jumping through screens left and right. So we're going to go ahead, press send keys. And now notice that we're iterating through all the known attention identifier keys, again, in hopes of finding hidden functionality. So we'll let that run for a second. Shouldn't take long. Okay, and eventually we found a hidden attention or a hidden screen corresponding to a hidden attention identifier key. But if we want to see what key it was, we do have, again, the extensive logging capabilities. Here we see all of the attacks that we ran, effectively everything we've sent to and from the mainframe. I'll go to the last attacks here. Okay, so every time we toggle the hack fields, we'll see exactly what the settings were. So if we had remove field protection enabled or show hidden fields enabled, we'll see exactly what our settings were. And then down here, we'll see the EPSIDIC encoded payload that's sent to the terminal. And notice that when I toggle between, let me see, I did all of that. When I toggle between the log items, I'll see in the terminal the exact screen that invoked. Okay, so it's sending that payload to the terminal every time we click each log item. So go to the last bit just to demonstrate the attention identifier keys. So everything we've done through the demo.
And it saves all of this in a project file. You can pass in a parameter to change the project file, but this is all actually saved in the folder of the tool, so you can always reference it later.
Yeah. So in the last few log items here, we see the attention identifiers that were sent, so we can just scroll through them until we see which attention identifier was responsible for invoking the hidden screen. In this case, it was the PA3, and it can also be invoked by sending the sysrec attention identifier. And I think that wraps up our demo. We were able to get through it.
Thank you. All right, so some closing thoughts, because I know that we covered a lot of stuff. The first thing that we want to discuss are mitigating these. There do exist a few mitigations. So the first one, IBM has a 3270 IDS. And we do recommend that you use it, but with the caveat that it can't detect malicious traffic from anomalies. It just goes, this isn't what we expected, so you'll have to fine tune it and play with it. It's not perfect. The next one is don't use application level authorization or authentication. You should be using system level stuff like RACF, Top Secret, ACF2. Just don't rely on application level. And unfortunately, a lot of these applications, again, were designed in the 70s and 80s, and you couldn't do this kind of thing back then. You were on a physical 3270 terminal, so they just didn't even think about this stuff. Don't hide, just don't use hidden fields really anymore, because anything that's hidden, we can just see it. Doesn't matter what it is, it's easy to see. And then you want to secure anything that you have within an attention identifier key. As John said, most of these weren't hidden out of malice or anything like that. It's just operators or developers would do it so they had an easy way to get back to something that they needed later on. But now we have the ability to enumerate through all of them relatively quickly. All right. So some key takeaways that we have for this. The first one is that mainframe computing is alive and well. It's not a dinosaur. It's one of the most important pieces of our modern infrastructure, and without it, like literally society as we know it would almost collapse. Like they are that important. The next one is that mainframe applications are not immune to security exploits. As we've demonstrated, these are not difficult attacks to exploit once you know how the protocol works and once you develop the tool to work on them. We have seen every one of these attacks in real CICS applications. Like these are not theoretical. We have literally seen every one of these multiple times. And then finally, there are now resources available for you as a security researcher to do this kind of research, specifically the DVCA Docker container. which leads me into my next slide, which is a special thanks to Phil, a soldier of Fortran. His work was instrumental in us even finding our footing and getting started. He's been there to support us as a mentor. Like I said, he worked with us on the DVCA. He is, one of the mainframe gurus out there. He has, as far as I know, the only offensive security mainframe course out there, known as Evil Mainframe Training. He has given 10 plus years of talks on mainframe hacking, so you can just go to YouTube, look it up, see all of those talks. And then he also runs the Internet Mainframes Project, which is a Tumblr account that shows screenshots of internet-facing mainframes and CICS applications. So we're going to leave our contact information up here. As you can see, we created a Discord channel. I'm sure there's going to be questions, and a lot of this stuff gets complicated, as you might realize, so we may not be able to handle it during a Q&A. So feel free to join the Discord channel and ask any questions that you may have. But with that being said, thank you very much. So questions? Okay. Well, thank you.
Thanks, everyone.
Oh, yeah, sure. Yeah, oh, sorry. Yeah, my bad. I don't know, 50 or...
Over 20,
Right.
certainly. I
More
would say
than-
about
Yeah,
to
probably
50.
closer to 50.
Yeah.
Yeah.
Out of that, we're not picking up that microphone. Can you verify that it's on?
We've looked at about 50 CICS applications. The question was, how many
Test,
CICS
test.
applications have we taken a look at?
Yeah, because
At
I
this
have a
point, it's-
follow-up to see if, your sample set for the answer on the next one.
Yeah.
Right, it's been about 50 CICS applications, I would say, roughly.
Okay, out of those, on the enumeration attacks, are you seeing at all that the developers were doing like a timeout or block because, oh, you hit N number, or no, because the assumptions of the environment at the time with fixed terminals?
I would have to assume it's the assumptions of the time, but no, we have never had anyone reach out to us or have problems with that or detect it.
And the applications never said like, oh, you're in a timeout period, that's all.
No,
That's
we never
amazing.
once had, we've generally been able to do this undetected. for the
And you
most
can
part.
just iterate away, and it's just like, yeah, keep trying, man.
Right.
Cool, thank you.
Thank you.
Hi. I recognize that Telnet's kind of inherently insecure, but I was just wondering about, for just communicating over TCP, if there's any like new developments in like maybe wrapping the connection protocol in something else, or maybe securing Telnet in any way.
There is encryption, but the thing is we're man-in-the-middling ourselves, and it doesn't really matter. So one of the options in the tool, actually, when you start the tool, if you are connecting to a server that supports TLS, there's a flag that you can pass in, and we still can do the same thing with a TLS encrypted server. Because again, we're man-in-the-middling ourselves, so we're in full control. And that is something that we probably should mention, is that this is more of an insider attack. This is not something that somebody outside of your company is going to do, because even though there are a handful of CICS applications that have been internet-facing, nearly all of them are internal only. So this is more of an insider threat kind of attack.
Okay, and for like outbound connections, you could just like wrap it in something else, I assume.
No, it's just TLS.
Oh,
yeah,
right. Okay.
And I believe one of Phil's talks, he mentioned that maybe half the mainframes he's worked with, he's actually seen that enabled. So it's still not enabled that frequently.
Oh wow.
Even though he's been talking about this for 10 years.
Okay, thanks. Great talk.
Thank you. Okay. Was there anything from chat? All right. Well, thank you so much.
Thanks, everyone.